Good morning, everyone. My name is John Gancarz, and the topic of my senior honors thesis was the investigation of micropulsations induced by injected electromagnetic waves, and I worked with Professor Lee. So here's a brief visualization of my project. Last summer, at the end of July, I went with Professor Lee and his research team up to Alaska, to Gacona, Alaska, to the High Frequency Active Auroral Research Program. There's a picture of it right up there. A little bigger. So this is a huge antenna array. This is around 33 acres of 72-foot high antennas, cross-dipole antennas. It can emit a frequency somewhere between like 2.8 and 10 megahertz. It has 3.6 megawatts of power available to it. It's a really, really impressive site. It's a government facility. It's used for a study of the ionosphere, which is the region of the Earth's atmosphere, which is ionized by solar radiation, and also it's for study of the plasma that's in the ionosphere as well. So this is where we performed our experiments, and I collected data here using a few diagnostic instruments, which I'll get back to. You may have heard something about this before. It's HAARP. There's actually like some conspiracy theories, like the government's trying to control the weather at this place. I can't confirm or deny that, but no, actually I can't deny that. What this affects are not the regions of the atmosphere that would have anything to do with our weather here on Earth. Only at higher elevations. And going back, so for our experiments, what we were trying to do is actually influence the local geomagnetic field to cause certain fluctuations to occur. And we did that and we measured these magnetic field fluctuations using a magnetometer, and we also used two different types of radar, primarily the radar called MUIR, the modular UHF ionospheric radar, which is at Gacona, and also a radar called SuperDARN, which is at Kodiak Island in Alaska. And these were measuring basically the plasma turbulence at the time of the experiment. So combining all of these diagnostic instruments, the information I got from those in the processing, with our own theoretical models, we come to my senior thesis, which what I was trying to prove is that at this radar facility, primarily we use two different types of waves, two different polarizations, and each of those polarizations cause different magnetic field fluctuations. So there's one called O-mode polarization, ordinary mode, that would cause fluctuations along the the east-west and the up and down components right here, whereas the other mode of the antenna, the other polarization we can emit, we expect to make magnetic field fluctuations along the north-south component and the up and down component. So I'll get into that a little bit more. Field background information, plasma, the fourth state of matter. As we've learned, it's something that's macroscopically, it's quasi-neutral, but when you get right down to the particle level, we have ions and electrons which are free. And this creates all sorts of interesting effects within a plasma, because not only do you have the collisions, but you also have the Coulombic interactions. You have the electric field between all these different particles, so it creates a lot of interesting phenomena. I showed a picture here of the atmosphere versus the ionosphere. This is the region, like I said, it's ionized by the rays from the sun. You can see this little green right here. That's where the aurora would be happening. I was in Alaska during the summer, so I didn't get to see that. It's all light almost all the time. But if I'm in the winter, maybe I wouldn't have gotten a chance to see the aurora. We're primarily concerned for this experiment with the F region of the ionosphere up here. What makes this like I put for the antenna array that I showed you before. It's an ideal region to study plasma, because on Earth we can create plasma in a lab, like sustained plasma, well, like fractions of a second. But here we have plasma continuously there all the time. It's an ideal laboratory because there's no boundary conditions. We just have all this plasma in the atmosphere, and that's what we're using an antenna array, like I showed you, to do experiments with that plasma. All right, I'll get into some of the wave interactions here. First, I'm going to mention something called the plasma frequency. In plasma, we have our free electrons, and if one of those free electrons get kind of moved, right, it would oscillate around a neutral position. So the frequency at which that electron would oscillate, we call that the plasma frequency. And here's our antenna array. It's called a heater, literally because it adds energy to the electrons in the ionosphere. the ions are comparatively a lot more massive, so it really doesn't affect the ions. So only the electrons are really influenced by this heater. And we have our wave going up here. I put the two different types of waves. O-mode wave, where the electric field at its reflection height is parallel to the magnetic field, whereas X-mode is perpendicular to the magnetic field. And I'll show you. So we have our incident wave coming up here, and at its reflection height, when this wave approximately matches the plasma frequency of the natural plasma up there, it decays via this thermal filamentation instability. It'll decay into a high frequency sideband and also an electrostatic wave, which I call here, I just call it I, or it means its frequency and wave number matching relationship, I right here. Basically this, for our electrostatic wave, I'll show it right here, here's O-mode electrostatic wave. It's going basically into the wall. And if you imagine almost like a sinusoidal wave of density, of electron density going into the wall. This is O-mode heating, this little geometry of the experiment. Like a sinusoidal wave going into the wall of density, we get these large plasma sheets forming in the ionosphere. These are like tens of kilometers in length, maybe 2 kilometers apart, 1 to 2 kilometers apart. And just imagine these sheets of high and low electron density in the plasma forming above our heater. So depending on which wave we emit, which polarization from the heater, either O-mode, I'll show you, X-mode, the configuration of the plates change, their orientation. O-mode plates will form perpendicular to the magnetic field, as you can see here, whereas X-mode plates would form parallel to the Earth's magnetic field. So here we would turn on our heater, and you'd see this heating occurring in the ionosphere. And one of the forces I want to mention here is a force on the electrons called the thermal pressure force. As this heating is going on, you see that there's a little arrow there. It's a result of the temperature changes of the electrons. And imagine, to go back to your physics 2 days, when we have a force acting on the electron, right? And we have a background magnetic field, approximately straight down in the polar regions, approximately going straight down. And when we have this electron moving this way, we do our QV cross B, right? And we would have electrons going either out towards us or back into the wall from this force. What's going on here is there are actually currents forming in the ionosphere around these big plasma sheets. So I show that here. Imagine we have currents, these delta J, I show currents right here, that we're going around the sheets, all right? So to bring everything together here, we have moving electrons, right? We have moving electrons changing densities. When we have moving electrons, we have currents, right? The ions are relatively stable. We have electrons moving versus the ions. And then when by Ampere's law, when you have currents, we have magnetic fields. If you imagine this to be sort of like a wire, right? You imagine the magnetic field going around this wire. We would expect fluctuations to happen for O-mode heating in the east-west and up and down directions. So we call that the D component and the Z component. So we hear delta D, delta BD and delta BZ. For X mode, our geometry changes because the plates are this way, the current loops are going this way, and we have fluctuations delta BH, delta BZ, which are the north-south and north-south and up and down directions. So bring it all together. By virtue of the fact that we have X mode heating, right? We would expect to see fluctuations, a correlation of fluctuations along the north-south and up and downward directions. For O-mode heating, we'd expect along the eastward direction and the up and down directions. So when I have these correlations, now I have my magnetometer. My magnetometer is on the ground. And now somehow I have to find these correlations amidst all of the other magnetic field information that's going on in the ionosphere, all the naturally occurring currents. What I have to figure out through data processing is how do I get out the correlations I want to see, the correlations I caused specifically by the heater. And the thing that's going to our advantage here is that the magnetic field fluctuations generated by the heater, by this huge antenna array, are only being formed in very specific components of the magnetic field. So for the O-mode heating, we would be looking for fluctuations caused by the heater only in the D and Z directions. This is O mode right here. For X mode, it would only be in the H and D directions, the northward and the downward, H and Z, the northward and also the up and down direction. So we're only trying to find here the signals from the current loop system within the plasma sheet structure. So what that entails is basically we take like an inner product, like a dot product between two different components of the magnetic field, imagine two different time vectors, and taking the dot product between those two, the inner product, and then subtracting a correction term, which is all the correlations, the natural correlations that aren't of interest to us, and focusing on only the ones caused by the heater. So we get, through data processing, this value right here. This is some of my data. We had some actually very good results from these experiments. This, I mentioned that there's two different types of modes of heating, O mode and X mode. These are continuous waves. There's also an O mode pulse, but that's used for radar. That's something a little bit different. But focus here on the blue here for O mode. As expected, the DZ correlation, the eastward and downward, we expect to see eastward and downward magnetic field fluctuations from O mode heating. And you can see that these are larger in the blue regions here. Similarly for X mode, we have this large peak right here, right at the beginning of when X mode is starting for the HC correlation. And it's relatively, there's no real correlation here during the O mode heating. You might look at this data and see that this is actually occurring a little bit before X mode. The reason for that is just by virtue of just because of the actual data processing technique. Each point here actually would contain information like around 5 minutes ahead of it, maybe a little bit less than that. So we actually would expect it to see like comic starting right before X mode, that heater actually changes into X mode. When the data is good enough, we can, so this correlation method showed me this, all right? But if the data is clear enough, we could actually go back to our actual, just the fluctuations. I show you just the signal power. And you can see even with your naked eye that they look similar, that there's comparatively, that here, for instance, for O mode, I highlighted here, you can see in the D and Z components, you can see these three peaks right here, right? But then for H, you don't have a clear correlation here. These are obviously correlated, and this one isn't. So for radar detection of our plasma sheets, this is to see that the phenomenon of interest is actually occurring at this time. These are these high and low density regions, which we call plasma sheets, or also parallel plates, we call them as well. So there's actually naturally occurring electric fields in the atmosphere, and those interaction with the background magnetic field will cause these plates to drift, right? Called the westward drift right here. And it will drift right in front of our radar beam. This is one of the radars at Gakona. It's called Muir. And these will drift right through. And we should be able to see, this is a range time intensity plot. And this was past results. We should be able to see these stripes on our graph by these sheets passing by the radar beam. This is very good data. This is from Professor Lee in 1995, I believe. And this is at Arecibo, which is a very, I had the opportunity to go there last summer and this past winter. It's a very sensitive antenna. I mean, right, versus very sensitive, like radio telescope versus what we're using in Gakona with our radar. It's a lot more sensitive radar. So we found really nice data in Arecibo. And HARP previously, something like this would have been found. You can also see these stripes of these plasma sheets moving past. This isn't as kind of sensitive as Arecibo. It's got a wider beam angle, but we can also see the plates of interest here. It detects something. It doesn't exactly detect the density. Arecibo was able to detect the density of the plasma, create a density profile. This detects something a little different. I won't get into that so much, called parametric decay instability. But then for our own data, I'll show you this. This is data that I processed during our experiments. This is the mode of the heater. What is the heater doing? We have the O mode continuous wave and X mode continuous wave. Then we have something called the O mode pulse. That's something just for the radar, just to generate like this PDI, this parametric decay instability. And this is actually very good data because we see that right along the bottom here during our O mode heating, it actually kind of decays right here. you can see that we have this PEI occurring. We have this backscatter occurring at a low altitude, but also at a high altitude. The way the radar was configured for this experiment, it wasn't, the beam angle wasn't on an angle like I showed you in the previous slide. It was kind of more straight up. So as these sheets were passing, we weren't necessarily expecting to see really nice slants coming down, but we see a little bit of that right here during our O-mode heating. X-mode heating is a little bit a different configuration. We actually don't expect to see anything, which for the large part we don't, which is good. Right when we change into X-mode, there's a little bit of turbulence. You can see, you can barely see a little bit right here. And then as we continue in time, as the mode changes here, we can also see this region up here. And these are mostly, actually, if you get really close to them, they're more flat. And you can see the kind of two little sheets here. That's actually a different phenomenon, not related to my thesis occurring here. Something called cascaded Lamier waves. I won't get too into that. But basically here, the exciting thing is that both at two different altitudes, we get this parametric decay and stability occurring, which is really good evidence for these plasma sheets. One of the other radars we use is SuperDARN. This is at Kodiak Island in Alaska. It basically kind of sweeps all over Alaska. Its radar beam, I think it's 10 megahertz. And this data shows what we expect to see here is for O-mode sheets, I mentioned those are parallel to the magnetic, those are within the meridian plane, whereas X-mode is perpendicular to the meridian plane. So for these plates that are parallel within the meridian plane, we expect the beam to kind of pass right through it, not get too much backscatter. But when it's perpendicular, we expect to get backscatter. At the altitude of interest right here, we do see that where it kind of goes through here, but here we get more backscatter. I'll just briefly mention just future research going on from here. There's a lot of different ways we could go with this. Professor Lee's two new instruments, the Geomagnetic Observatory System is the name of those. These are his own magnetometers, which we could use for data research instead of the ones that were just at the facility. They're very sensitive. Then we can see how we could also look at how the magnetic field fluctuations are related to the plasma conditions at that time. We could also always change the mode of the heater, that huge antenna array, and see how that would affect the fluctuations, use different heating schemes, see how the radar would also respond to that. There's also a new heater that's being built at Arecibo. The previous one was destroyed by a hurricane, actually, so they built a new one there, so more heating can be done there of the atmosphere. High frequency heating. And here's just some acknowledgements to Professor Lee. All my fellow researchers who helped me out quite a bit. It's a picture of me and some fellow researchers at the actual antenna array, and the ECE department, of course, for all of their generous support. So thank you very much. Any questions? Yes, please go to.
You have your experiments are done like in the tens of megahertz. How do you pick that frequency, or perhaps a related question is, what's the typical plasma frequency?
So the frequency is right around there. We actually go a little bit below. So it was around, for our heating experiments, it was around 10.8 megahertz. The plasma frequency was just around there, a little bit above there.
Okay.
All right, thank you very much.